Hello everyone, I am Ayoub Zumeit. I am a PhD student, member of the Printable Electronics and Sensing Technologies Group, based in the University of Glasgow in the UK. So in this talk, I will be presenting the work related to silicon nanoribbon-based printed transistors for high-performance flexible electronics. In this presentation, I'll, um, I will give you an overview of the motivation behind my work with respect to the recent advanced and emerging flexible electronics and applications, including some potential materials which can be selected to meet the high performance requirements for these applications. Then I'm going to talk about the printing techniques which we use in this work, followed by a detailed overview of the fabrication steps and structural characterization of the fabricated transistor. Then I will demonstrate the electrical characterization, followed by the electromechanical performance evaluation, and finally overall summary of this talk. The recent progress in flexible and printed electronics established the foundation for advancements in many emerging applications, including wearable electronics for healthcare services and flexible portable displays, implanted devices, sensor imaging, electronic skin, including robotics, prosthetics, and Internet of Things, etc. Along with the flexible form factor, many of these applications also require high device performance, which lead to fast computation and communication, make them suitable for machine-to-machine and or human-to-machine connectivity. In this regard, high-performance flexible CMOS-based processing units are needed so the data can be transmitted, collected, and processed fast. Likewise, wireless communication and wearable technologies, including electronic skin, medical healthcare systems, etc., requires a high-speed switching in ultra-high frequencies. Also, with the 5G, the impact will be tremendous, especially now with increasing the amount of data that can be transmitted wisely at high speed, so that will give the user access to their health information in real time. However, releasing such a devices and circuits on flexible substrates with the performance at par with the conventional microsilicon CMOS technology is a challenge because of the requirement of the high temperature especially when it comes to conventional inorganic semiconductor processing. In terms of the electrical performance of flexible transistors, here the performance is mainly based on its material mobility. The mobility of flexible transistors gains a significant interest since it has impact on several electrical parameters such as the current density, energy efficiency, and switching speed. In this regard, the printed devices and circuits based on the high mobility nanostructured materials such as the silicon carbon nanotube, graphene, etc., have been explored. Therefore, inorganic printed electronics could potentially provide a solution for high performance large area electronics. So when it comes to integration and assembly of nanostructures on flexible substrate, the transfer printing technique can provide a solution, especially it allows the nanostructures to be transferred from source wafer to receiver in high yield manner and with a good alignment. In general, this method can be done using a soft intermediate elastomer stamp. Printable single crystal silicon can be achieved, such as nanoribbons, can be achieved using SOI wafer, where the barium oxide layer serves as a sacrificial layer, as you can see here from the schematic. A major challenge here with the nanostructure-based devices is that some of the critical fabrication steps, for instance, the nanostructure fabrication and doping, a high-K dielectric, these steps require a high temperature that are incompatible with the flexible substrate. Therefore, it's important to develop and optimize device fabrication strategies in such that all the fabrication steps are carried out at low temperatures. In regards to the device fabrication process and the structure characterization of the printed transistors, here is the schematic of the processing steps of the P-type silicon nanoribbon field effect transistor fabricated by transfer printing method. Since the high temperature fabrication steps are such as selective doping are carried out before transfer printing, This method decouples the high temperature process steps from the low temperature steps, including the high K room temperature silicon nitride deposited gate dielectric and metallization for the to deposit metal contacts for the final device. That also can be carried out after transfer printing, and in order to realize the final form of the device on flexible substrate, as you can see here in this figure. So here is the structure. As you can see in this slide, the structural characterization of the p-type transistor at different stages. Figure A shows an optical image of the p-type doping profiles of the active regions, source and drain on the source wafer. Since achieving a doping is a challenge, once these structures are transferred, or once the structures are transferred on flexible substrate because of the thermal budget issue. So without heavy doping in source and drain, it's not possible to achieve an ohmic contact, and therefore realizing a transistor. So figure B demonstrates the SEM image of the anchored nanoribbons nanoribbon arrays before transfer printing on the donor substrate, where the buried oxide, as you can see, the buried oxide layer is silicon oxide underneath the silicon layer is removed by the etchant solution to form these suspended ribbons. Figure C shows the transfer printed nanoribbon arrays on commercial polyimide substrate, and the final figure shows the final form, the top view SEM of the top view of the final form of the silicon nanoribbon transistor. In terms of the electrical characterization of presented p-type silicon nanoribbon-based transistor, the electrical characteristics of the final device with the drain bias of minus 200 millivolt as shown in figure A. The current on and off ratio was found to be around 10 to power 3. The extracted subthreshold swing is around 600 millivolt per decade. Figure C shows that the transfer characteristics at different values of drain to source voltage. It's worthy to note that the threshold voltage VTH remains constant even when the VDS is changed. That shows that the high stability behavior. Figure C shows that the output characteristics obtained at different VGS, as it can be observed that the drain current increases as the negative gate bias increases, which confirms that it's a p-channel behavior of the fabricated nanoribbon field effect transistor. The table shows a summary of the n-type field effect transistor, which we demonstrated last year in Flips 2020, and this year we demonstrated this work, which covers the p-type silicon nanoribbon-based field effect transistor fabricated at room temperature, applying the same fabrication process. As you can observe that there is a variation in terms of mobility, which makes sense, and we expected that since the mobility is inversely proportional to the effective mass of the charge carriers, and the effective mass of the holes of positive charge carriers are much higher than of the electrons. So in the device stability was also evaluated under cyclic bending conditions at around 40 millimeter radius of curvature. 100 bending cycles were also performed as shown in figure B, and the variation of the maximum drain source current values corresponding to on-state current at minus 6 volt of the gate voltage and 1 volt of drain to source voltage. And to sum up, in this talk, we have demonstrated a room temperature fabrication process for a p-type silicon transistor on flexible substrate, and the p-type silicon nanoribbon-based FET showed an excellent performance even under cyclic bending tests, making them an excellent candidate for realizing a high-performance flexible CMOS circuits. So the optimized process flow is based on the CMOS technology, and it could be extended for other nanostructure nanoribbons based on different other high mobility materials to realize the field effect transistors. and such as gallium arsenide, gallium nitride, and indium arsenide, etc. So here I would like to thank the group that I'm in. Also, I would like to acknowledge the funding gender support. And thank you very much for your listening and for watching my presentation. And it's been a pleasure to present my work in FLIPS 2021. Thank you.